Hi, I'm Barry Olney from In-Circuit Design. This is a demonstration of the IPC-2581B bi-directional interface from Cadence OrCAD PCB and Allegro PCB into the ICD Stackup planar software. First of all, I'll open up a new Stackup in the Cadence cross-section editor. Now the default is a two-layer board, so what I'll do is I'll add two layer pairs to this, and we'll call these internal layer pairs planes, and the top one will be a ground plane, and the one below that will be a power plane. And I'll rename the dielectrics to a core in the center because we want to beef up the center of the board, and a prepreg on the dielectrics. And we also need solder mask top and bottom, so I'll add a layer and I'll find a mask which is solder mask top and has a layer function of solder mask with a solder mask material. And I'll do the same for the bottom. This time we'll add below, and solder mask bottom, layer function solder mask, and a solder mask material. So there we have a 4-layer board, and we have two planes in the center, signal layers on top and bottom, and covered in solder mask. And you can see here the Cadence software has put in the default dielectric constants and trace width. We could adjust this to get the impedance, which gives us around 50 ohms, but unfortunately Cadence doesn't transfer the trace width or clearance with the IPC-2581B data. So when we import that into the ICD Stackup planar, we will not receive the trace width and clearance. I'll now export this to, I'll call it a 4-layer XML, and I'll open up the ICD Stackup planar, and we'll import Allegro file, 4-layer XML, and here's the file we just created in Cadence. Now I can add the trace width and clearance to it, so we get some impedance numbers. And you can see here we have roughly 50 ohms single-ended characteristic impedance and around 100 ohms differential edge coupling impedance. Now, the advantage of the ICD Stackup planar is it has a huge library, and our library contains over 33,250 dielectric materials, rigid and flexible materials, up to 100 gigahertz. So what we'll look at is just 1 gigahertz material, and I've selected an isola material here. We have probably 60 different material vendors in the library, but isola will do for this demonstration, and we use a 370 HR material. Now on the top prepreg here, we want a 8mm material. It's this one here, so I'll double click that and we'll insert it into the Stackup, and we'll do the same for the bottom prepreg. And for the center dielectric, we want to beef this up because we only have 28.8 mil thickness of board thickness, total board thickness. So we'll beef that up to about 42. So down here, find a 42 dielectric thickness, and we'll insert that from the library. So here we have a board that's now 62 mil thick, which is pretty standard, and we have the prepreg and core materials set up, and we also have our impedances of 53 and 100 ohms. So I'll now export this, and we'll call this 4-layer ICD, and I'll again open up the cross-section editor in Cadence, and we'll import this cross-section there. And you can see this time that I import it, that it's actually bringing the trace width in. So we have the impedance of 53 ohms, just as we had in the ICD Stackup planar. By the way, Cadence also uses a 2D boundary element method field solver, the same as we use in ICD. Of course, it was written by different people, so there are slight variations. Now, that's one way to go about it, starting in Cadence and extracting the Stackup information into the ICD Stackup planar, and then editing the file and putting it back into Cadence. But of course, the easiest way to do it is to start with the ICD Stackup planar. So here we have a 10-layer DDR freeboard, which I've previously done, and we've added all the Isola 370HR materials to it. If we now export this to Allegro, and I'll call it a 10-layer DDR3 XML, and go back to Allegro and import this file. You can see that all the 10 layers have been added, including solder mask. We also have the impedances calculated from the dielectric materials from the ICD Stackup planar, giving us the correct dielectric constants and trace width for a particular signal, which gives us a more accurate calculation. Thank you very much.